Arjun, we've talked about the transformer architecture before, even its generalization, but there's a fascinating twist that connects it to everything.
Exactly, Maya. The core idea we explored in hashtag TCM183005, that attention mechanisms alone could form a neural network, was just the beginning. It's truly a universal computational primitive.
When we first learned about attention is all you need, it was revolutionary for NLP. But what exactly was it replacing, and why was that so surprising at the time?
The paper starts by stating that dominant models for sequence tasks were based on complex recurrent or convolutional neural networks. These architectures had inherent limitations.
Recurrent networks process data sequentially, making them slow for long sequences. Convolutional networks struggle with long-range dependencies. The transformer proposed a radical shift.
So, the attention mechanism that was previously just a component in those models suddenly became the entire architecture?
Precisely. The paper states, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. This was the audacious claim. Attention alone is sufficient.
Dispensing with both recurrence and convolutions entirely? That must have sounded impossible to many people when this paper first came out.
It did. The common pitfall was thinking attention was just a weighting scheme, but it's a powerful way to model dependencies directly rather than through sequential processing or local kernels.
So the previous models had an attention component, but not an attention-only architecture. That's a crucial distinction for the transformer then.
Indeed. In TCM 033005, we saw how attention allowed parallel processing. This is a direct consequence of dispensing with recurrence. No more waiting for the previous step.
That parallelization meant faster training, right? Which was a huge bottleneck for those complex recurrent models.
Look at the machine translation tasks. The transformer didn't just match performance. It set new state-of-the-art records, like 28.4 BLU on the WMT 2014 English to German translation task.
And it did so while being significantly faster, like training 3.5 days on 8 GPUs for French to English, a fraction of previous costs.
Think of it like this. If you have a team building something, you can either have everyone work on one step at a time or split tasks so many can work simultaneously. Attention enabled the latter. This analogy highlights the parallel processing benefit. However, it doesn't fully capture how attention also dynamically decides which contributions are most relevant for each subtask or how the information is blended for a richer output representation.
So it's not just about what it can do, but how efficiently it can do it for large-scale problems. That's a strong incentive for adopting it.
The ability of attention to model global dependencies and enable parallelism made it a breakthrough for NLP. But the true genius is its adaptability, as we'll see next.
So the all-you-need part isn't just about NLP. It hints at something much broader. Let's see how this single idea became so versatile.
In TCM 213005, we touched upon the transformer's generalization. This illustrated transformer post helps us visualize how that core attention mechanism works.
This visual breakdown is key. The original paper can be dense, but seeing the pieces flow together makes it much clearer.
At a high level, the transformer takes an input sequence, like a sentence, and processes it through an encoding component and a decoding component to produce an output.
So the black box view from earlier is now opened, revealing these two main parts, each made of stacked layers working in concert.
Each encoder layer has two sublayers, a self-attention layer and a feed-forward neural network. This structure is repeated, processing the output from the layer below.
And the important part here is that the feed-forward layer does not have those dependencies, meaning it can run in parallel for each position.
Let's take the sentence, "The animal didn't cross the street because it was too tired." When encoding it, how does the model know if it refers to street or animal?
A human understands the context, so self-attention must be how the model gains that contextual understanding across the sentence.
Self-attention allows the model to look at other positions for clues. It does this by creating 3 vectors for each word: query, key, and value. These aren't just arbitrary vectors. They're created by multiplying the original word embedding by 3 different learned weight matrices during training. These 3 matrices that we trained during the training process allow the model to learn what aspects of a word constitute its query, key, and value. Query, key, value.
This is the foundation we first saw in hashtag TCM003005, where attention was described as a learned lookup process. How do these vectors work together?
To find how much focus to place on other words for a given query word, we calculate a score by taking the dot product of its query vector with every other word's key vector. To keep gradients stable and prevent very large scores, and echoing what the source mentions as a 3rd and 4th step, we also divide the scores by 8, which is the square root of the key vector's dimension, before normalization. This scaling is crucial.
So, query and key vectors determine the relevance or how much one word attends to another. Higher dot product means stronger connection.
These scores are then normalized using softmax, making them importance weights summing to 1. Then, multiply each value vector by the softmax score.
So the value vector contains the actual information, and the softmax scores tell us how much of that information to blend in from each word. It's like a weighted average, but a highly dynamic one. The weights are contextually determined, and the items being averaged are rich factor representations rather than simple numbers. This blending creates a highly nuanced, context-aware output.
This weighted sum of value vectors, where query and key define the weights, is the core of self-attention. It's not just a lookup table, it's a dynamic, learned interpolation.
That's a crucial distinction. It's not just retrieving one item, it's creating a new, context-rich representation by blending information from the entire input.
This process, repeated for each word and then summed, forms the output. It allows contextual understanding without sequential processing. Next, we'll see its broader historical context.
Okay, so the query key value mechanism enables this parallel contextual blending. How did this idea of attention itself evolve into this form?
Before the transformer, attention wasn't a standalone architecture. This post by Lillian Wang beautifully traces the evolution of attention mechanism in deep learning.
So the transformer built on existing ideas. It didn't invent attention, but showed it could be the sole mechanism for a powerful model.
Attention is motivated by how humans focus. We pay visual attention to different regions of an image or correlate words in one sentence. It's about selective focus. While this is a useful high-level analogy for selective prioritization, it's important to remember that transformer attention is a mathematical computation of relevance, not a conscious cognitive process, and it operates across all elements simultaneously.
Like focusing on an animal's ear in an image while ignoring the background, or predicting a food word after eating. It's about relevance.
Early sequence-to-sequence models for tasks like translation had a problem: incapability of remembering long sentences. They'd forget the beginning of an input.
This was the bottleneck of the fixed-length context vector, right? All the information had to be crammed into one summary, losing detail.
The attention mechanism was born to solve this. Instead of a single context vector, it created shortcuts between the context vector and the entire source input.
So the decoder could dynamically look back at any part of the input, not just a summarized version. That's a huge shift in how information flows.
The definition section shows the context vector is a sum of hidden states of the input sequence, weighted by alignment scores. These scores are crucial.
So the transformer's query key value system is a specific way to calculate those alignment scores, or weights, deciding what parts of the input are most relevant.
The alignment model assigns a score alpha of ti to each input-output pair. These weights define how much of each source hidden state should be considered for each output.
This is a direct parallel to the softmax scores we just saw in the illustrated transformer, determining how much each value vector contributes to the final blend.
So the attention mechanism is incredibly powerful, enabling context and parallelism, but it's not a silver bullet without its challenges. For instance, notice how our detailed explanation relies on tokens and their positions?
Right. What if your data isn't easily broken into discrete tokens like a raw audio stream? Or what happens if you have an extremely long sequence?
Exactly. Tokenization itself can be a complex design choice, especially for novel data types. And for very long sequences, the self-attention calculation scales quadratically with sequence length, making it computationally expensive. That's a significant practical limit often addressed by more efficient attention variants.
And without positional encodings, the vanilla transformer would lose all sense of order. It's inherently permutation invariant, which is powerful for mixing, but a limitation if you need to strictly preserve sequential information without external encoding.
These historical insights highlight the ingenuity of making attention the sole mechanism, and understanding its evolution helps us appreciate its current impact.
So, from overcoming RNN limitations to achieving state-of-the-art results across domains, the transformer truly leveraged attention in a way that changed everything.